Hi everyone! Welcome to the new episode of Mathfinity, where math learning is fun and exciting. I am Giancarlo T. Rivera. Together, we will learn mathematics and conquer problems dealing with it. For this video, we will be guided by the Most Essential Learning Competency number 2 of Mathematics 10, which is Illustrating Arithmetic Sequence. Our enabling learning competency which will help you achieve this competency is performing operations on rational numbers. Before we proceed to our formal lesson, let's have a quick recall on what we learned from the previous video. We learned that pattern is a series or sequence that repeats. Math patterns are sequences that repeat based on a rule, and a rule is a set of ways to calculate or solve a problem. Secondly, a rule is pattern used to find the value of a term in a sequence. Next, sequence is a function whose domain is the finite set 1, 2, 3 until n, or the infinite set 1, 2, 3, and so on. And to evaluate the n term of a sequence given a rule, let the desired n term to be the input value of the given function or rule. To continue, let's have a review quiz. For each infinite sequence generated by the given rule, state whether all, some, or none of the terms are multiples of 5. You will be given 20 seconds to answer. Let's have sequence number 1, which is f of n is equal to 5n plus 10. 20 seconds, start now. Time's up! Let's now check whether your answer is correct. The answer is all. All of the elements or the terms generated by the function of n is equal to 5n plus 10 are divisible by 5. Why do you think so? If you're going to analyze this rule, we have two addends. The first addend is 5n, the second addend is 10. Both of these addends are divisible by 5. Therefore, if you take the sum of these two addends, of course, it will be divisible by 5, or all the terms generated by the function will be divisible by 5. To further explain that, let's evaluate some of its terms by letting n as any value in set of counting or natural numbers. For example, if n is 1, what is the value of the term or the first term? We let n is equal to 1. Therefore, 5 times 1 is 5 plus 10 is 15. And 15 is divisible by 5. So let's say n is equal to 2. 5 times 2 is 10, plus 10 is 20. And 20 is divisible as well by 5. And any counting number evaluated in this function will be divisible by 5. Is that clear? Let's proceed to sequence number 2. A sequence generated by the function f of n is equal to 10n. 20 seconds, start now. Time's up. Let's check. The answer is all. What do you think makes the terms divisible by 5? Yes, because of the factor 10. Because 10 is divisible by 5, all of the terms generated by this rule will be divisible by 5. Is that clear? Let's proceed to sequence number 3. Sequence number 3 is generated by the function f of n is equal to 5n minus 1. 20 seconds, start now. Okay, time's up. Let's now check whether your answer is correct. The answer is none. None of the terms generated by this rule is divisible by 5. Can you think what is the reason why none of the terms are divisible by 5? If your answer is because of minus 1, you're correct. The terms generated by this rule is either ending with a digit 4 or 9 because of the expression minus 1. To verify our answer, let's identify some of the terms generated by this rule. Let's take n is equal to 1, so meaning to say, we are evaluating the first term. When n is 1, 5 times 1 is 5, minus 1 is 4. When n is 2, 5 times 2 is 10, minus 1 is 9. When n is 3, 5 times 3 is 15, minus 1 is 14. So, if you're going to analyze the pattern or the rule, all the terms generated by this function or rule is either ending with 4 or 9. Is that clear? Let's proceed to sequence number 4. F of n is equal to 10 times the quantity of n plus 1. 20 seconds, start now. Time's up. Let's now check your answer. The answer is all. Obviously, all of the terms generated by this rule are divisible by 5 because of the factor 10. 10 is divisible by 5. Last sequence. Sequence number 5. F of n is equal to 3n plus 1. 20 seconds, start now. Time's up. Let's now check your answer. The answer is some. Not all the terms generated by the rule is divisible by 5. At what value of n do you think the terms will be divisible by 5? That's right. If the value of n ends with the digit 3. If any value of n, which is set of counting numbers, which ends with digit 3 is multiplied by 3, it will have a product whose last digit is 9. And if this will be added by 1, this will make the value of the term divisible by 5. For example, if n is equal to 3, we are evaluating the third term. So 3 times 3 is equal to 9 plus 1 is equal to 10. And 10 is divisible by 5. When n is equal to 13, we are evaluating the 13th term. Therefore, if we use n as 13, 3 times 13 is equal to 39 plus 1 is equal to 40. And we know that 40 is divisible by 5. And this pattern will continue. Is that clear? I hope it is clear. Did the quiz make you remember what you learned from the previous video? That's great! Let's now proceed to our actual lesson for this video. And that will be all about arithmetic sequence. And to continue this video lesson, let's establish our lesson objectives for this session. First, at the end of this video, you shall be able to define arithmetic sequence correctly. Secondly, you will be able to solve for the common difference of an arithmetic sequence. And lastly, you will be able to identify which sequence is arithmetic or not. Before we define what is arithmetic sequence, let's have trivia. Guess what? These are frozen leftovers from the formation of the solar system composed of dust, rocks, and ices. They range from a few miles to tens of miles wide. But as they orbit closer to the sun, they heat up and spew gases and dust into glowing head that can be larger than a planet. This material forms tail that stretches millions of miles. Do you already know what's being described? That is comet. Do you know what is the latest comet which had a closest approach to the sun? That is Neowise comet. Did you witness the perihelion of this comet? Due to its magnitude of brightness, most of the spectators were able to see the grandeur and magnificence of this once-in-a-lifetime experience through naked eye. Neowise comet is the brightest comet to appear in northern hemisphere skies in nearly quarter of a century. Comet Neowise, also known as C/2020 F3, was discovered on March 27 by astronomers during the Neowise mission, which used NASA's Wide Field Infrared Survey Explorer space telescope to look for near-Earth objects like asteroids and comets. The comet made its closest approach to the Sun, called perihelion, on July 3. At the time, it swept to within 29.4 million miles, or 44.1 million kilometers of the Sun, or inside the orbit of Mercury, the innermost planet. Because of its tail, it looked like the Tiamat comet in the anime Kimi no Nawa, which fell onto the town of Itomori, where people were having a festival. Until Neowise comet, Halley's comet is arguably the most famous comet. It is a periodic comet and returns to Earth's vicinity about every 76 years, making it possible for a human to see it twice in his or her lifetime. The period varies from appearance to appearance because of the gravitational effects of the planets. It was named after the discovery of English astronomer Edmund Halley in 1758. Because of its popularity, NASA even set up countdown timer to await the next approach of this comet to the Sun. If we are going to analyze the periodic behavior of Halley's comet perihelion, we can guess the next year of appearances of this comet. Considering the first appearance was in the year 1758 and its period as 76 years, the second, the third, and the fourth appearances will be 1834, 1910, and 1986 respectively. Based on this table, we can see relation between n appearances and year of appearances of Halley's comet. We can say that the first appearance of Halley's comet was in 1758, the second appearance was in 1834, the third appearance was in 1910, and the fourth appearance was in 1986. By making the year of appearances as terms of a sequence, we have now an example of arithmetic sequence. The first term of the arithmetic sequence is 1758, the second term is 1834, the third term is 1910, and the fourth term is 1986. So based on this sequence, how will we define arithmetic sequence? Arithmetic sequence is a sequence where every term after the first is obtained by adding a constant d. This constant d represents the value of the common difference. And for this example, the value of d is equal to 76, which is the period of Halley's comet. Earlier, we let the first appearance of Halley's comet as 1758. This represents the first term of the sequence. To get the second term, we will add 76 to it, and that will be 1834. This 1834 represents the second term. And this pattern will continue to get the next succeeding terms. So that means, if we are going to identify what will be the third term, we will add 76. And that will be 1910 added by 76. That's 1986. And again, added by 76. That will be 2062. As you have observed, we just continually added 76 to 1758 to generate the terms of arithmetic sequence. So we are already done defining what is arithmetic sequence. But how do we define common difference? Common difference is the difference between any two consecutive terms of arithmetic sequence. Remember, any two consecutive terms. In symbol, common difference is equal to a sub n minus a sub n minus 1, where d is the value of the common difference and a sub n is equal to nth term, while a sub n minus 1 is the term before nth term. Let's consider the previous arithmetic sequence as an example. The terms of the sequence are the years of appearances of Halley's comet, which are 1758, 1834, 1910, and 1986. Remember, The formula for the common difference is equal to a sub n minus a sub n minus 1. Thus, we need to identify any two consecutive terms and solve for its difference. Or, it is simply any term subtracted by its previous term. Let's identify pair of consecutive terms. Can you identify the first two consecutive terms in the sequence? Those are 1758 and 1834. So, we need to solve for its difference. So, we let n term as the second term, which is 1834. What is its previous term? The previous term is 1758. So we need to solve for the difference of these two terms. That is 1834 or 1834 subtracted by 1758 is 76. So the difference of the first two consecutive terms is 76. Let's proceed to another pair of consecutive terms. 1834 and 1910 are consecutive terms as well. So we need to solve for its difference, for their difference rather. The third term is 1910. What is its previous term? The previous term is 1834. So solving its difference, 1910 minus 1834, the answer is 76. And lastly, the last pair of consecutive terms are 1910, which is the third, and 1986, which is the fourth term. So again, we need to solve for its difference, for their difference rather. So, the fourth term is 1986. What is the value of its previous term? That is 1910. Solving their difference, that is 1986 subtracted by 1910, the answer is 76. What can you observe in the difference between any two consecutive terms of an arithmetic sequence? Yes, they are equal. That's why it is called common difference, meaning to say the difference between any two consecutive terms are equal. In this exercise, try to solve for the common difference of the following arithmetic sequence. You are given 2 minutes to accomplish this task. 2 minutes, start now. Time's up! Let's see whether you got the correct common difference for each arithmetic sequence. Number 1. The first two consecutive terms of this sequence are 31 and 33. The previous term of 33 is 31. Subtracting them, the answer is 2. The next consecutive terms are 33 and 35. The previous term of 35 is 33. Their difference is 2. The next two consecutive terms are 35 and 37. The previous term of 37 is 35, and their difference is 2. And the next two consecutive terms are 37 and 39. And finally, their difference is 2. Therefore, the common difference in number 1 is 2. Number 2. The given sequence is 7, -3, -13, -23, -33, and so on. Before you can answer the common difference correctly, you must remember how to subtract signed numbers. Let's recall the rules for subtracting signed numbers. First, change the sign of the subtrahend. If the given sign of the subtrahend is positive, change that into negative. If the given sign of the subtrahend is negative, change that into positive. Secondly, proceed to the rules of addition. Number 3, if they have like signs, simply add their absolute values and indicate their common sign. If they have unlike signs, subtract the smaller absolute value from the larger absolute value, then indicate the sign of the number which has larger absolute value. Or just simply recall that subtraction of signed number is equivalent to adding its negative. Let's try to apply the rules. The first two terms are 7 and -3. The previous term of -3 is 7, so we will subtract 7 from -3. -3 minus 7. So we will change the sign of positive 7. So that will become -7 and proceed to addition. -3 plus -7. Since both the addends have negative sign, we are expecting the answer to have negative sign as well. So to find the final answer, take the absolute value of both addends, then add. The absolute value of -3 is 3. The absolute value of -7 is 7. So 3 plus 7 is 10. So therefore, the final answer is -10. Let's now proceed to the next two consecutive terms of the same sequence. The previous term of -13 is -3. Subtracting them, that is -13 minus -3. Applying the rules, we will change the sign of the subtrahend, -3, into its opposite sign. So that will become +3. Then proceed to addition. That will become -13 plus 3. Since we have unlike signs, we will indicate the sign of the addend which has greater absolute value. In this case, the addend which has greater absolute value is -13. So we are expecting the answer to bear negative sign. Then, subtract their absolute values. The absolute value of -13 is 13. The absolute value of 3 is 3. So 13 minus 3 is 10. Therefore, the final answer is -10. Next two consecutive terms are -13 and -23. The previous term of -23 is -13. So our subtrahend is -13. Again, applying the rules, change the sign of the subtrahend into its opposite. That will become negative 23 plus 13. Since negative 23 has greater absolute value compared to 13, so we are expecting that the answer will bear negative sign. Then, take the absolute value of both addends, then subtract. The absolute value of negative 23 is 23. The absolute value of 13 is 13. So 23 minus 13 is 10. Then, indicating the sign, that will become negative 10. And the same process will be done in the next consecutive terms. So as you can see, we have common difference of negative 10. Number 3. The given sequence is 4.3, 5, 5.7, 6.4, and 7.1. The first two consecutive terms are 4.3 and 5. The previous term of 5 is 4.3. Therefore, we subtract them. That is 5 minus 4.3. And that is 0.7. The second two consecutive terms are 5 and 5.7. We subtract them. 5.7 minus 5, and that is 0.7. And it will continue. The next two terms are 5.7 and 6.4. The previous term of 6.4 is 5.7. 6.4 minus 5.7, the answer is 0.7. And lastly, the two consecutive terms are 6.4 and 7.1. 7.1. The previous term of 7.1 is 6.4. Subtracting them, that's 7.1 minus 6.4, that is 0.7. Therefore, we can clearly say that the common difference of this sequence, of this arithmetic sequence, is 0.7. Number 4. The given sequence is 5, 17 over 4, 7 halves, 11 over 4. The first two consecutive terms are 5 and 17 over 4. The previous term of 17 over 4 is 5. By subtracting them, that is 17 over 4 minus 5. Let's recall how to perform operations on fractions. Seventeen over 4 minus 5 is the same as 17 over 4 minus 5 over 1. In able to simplify this, we need to find the LCM of the denominators 4 and 1. And that will be our least common denominator, or LCD. The least common multiple of 4 and 1 is 4. Therefore, the least common denominator is 4. By continuous evaluation, that will be 4 divided by 4 is 1, times 17 is 17. 4 divided by 1 is 4, times 5 is 20. Then copy the operation symbol. That is 17 minus 20 over 4. And 17 minus 20 is negative 3. Therefore, the answer is negative 3/4. Next, 17 over 4 minus 5 can be simplified by identifying fraction having a common denominator as 4 and which has an equal value as 5. What fraction has a denominator of 4 and an equivalent value as 5? That is 20 over 4, because 20 over 4 is the same as 5. And that 20 over 4 has the same denominator as 4. Therefore, you can just simplify that as 17 over 4 minus 20 over 4. Since they have the same denominator, you just perform the operation on the numerator. And 17 minus 20 is negative 3, then copy the denominator, that's 4. Therefore, the common difference is negative 3/4. Let's continue verifying that the common difference is negative 3/4 on the next two consecutive terms. The next two consecutive terms are 17 over 4 and 7 halves. The previous term of 7 halves is 17 over 4. By subtracting them, that is 7 halves minus 17 over 4. Again, we need to find the least common multiple of 2 and 4 to find the least common denominator. And what's the least common multiple of 2 and 4? That is 4 as well. By continuous evaluation, that's 4 divided by 2 is 2 times 7, that is 14. Then, 4 divided by 4 is 1 times 17 is 17. Then, just simply indicate the operation, subtraction. 2 times 7 is 14 minus 1 times 17, that is the same as 14 minus 17. So simply evaluate what's the numerator. It's 14 minus 17 is negative 3. Then the answer is negative 3/4. Let's continue to the last consecutive terms. That is 7 halves and 11 over 4. The previous term of 11 over 4 is 7 halves. By subtracting them, that's 11 over 4 minus 7 halves. Again, find the LCM of 4 and 2, and that will serve as our LCD. By continuous evaluation, that will become 4 divided by 4 is 1 times 11, that's 11. 11 times 1. Next, 4 divided by 2 is 2 times 7, that is 14. Then simply evaluate the numerator, that will become 11 minus 14 over 4. And 11 minus 14 is negative 3. Therefore, the answer is negative 3/4. And as you can see, our common difference for this arithmetic sequence is negative 3/4. Number 5. The given sequence is x plus 3y, 4y, 5y minus x, and 6y minus 2x. In this example, the terms of the sequence are represented by algebraic expressions. Remember, terms in a sequence are separated by comma. So do not be confused in identifying the terms of the sequence. Let's now solve for the common difference of this sequence. The first two terms of this sequence are x plus 3y and 4y. The previous term of 4y is x plus 3y. By subtracting them, that is 4y minus x plus 3y. Remember, subtraction is just the same as adding its negative. Therefore, when we subtract this subtrahend x plus 3y, we must take its opposite sign. So that will become 4y plus the opposite signs of this subtrahend, and that is my negative x minus 3y. Then continue evaluating this by just combining like terms. 4y is the like term of minus 3y. By combining them, that's 4y minus 3y, that is y. Since x does not have terms similar to this, similar to it, you just leave that as minus x. Therefore, the answer is y minus x. Let's continue verifying that the difference in the next succeeding terms is y minus x. The next two consecutive terms are 4y and 5y minus x. The previous term of 5y minus x is 4y. By subtracting them, that's 5y minus x minus 4y. Then, that is the same as 5y minus x plus negative 4y, taking the opposite sign of the previous term, which is the subtrahend. So that will become negative 4y. Then proceed to addition. Then identify like terms and combine them. 5y is similar to the term minus 4y. 5y minus 4y is equal to y, and since minus x or negative x does not have terms similar to it, leave that again as minus x. That will become y minus x. Let's now proceed to the next two terms. The next two terms of the sequence is 5y minus x and 6y minus 2x. The previous term of 6y minus 2x is 5y minus x. By subtracting them, that is 6y minus 2x minus the quantity 5y minus x. That will become 6y minus 2x plus the opposite of this subtrahend 5y minus x, which is negative 5y plus x. Then, identify again like terms, then combine them. The like term of 6y is negative 5y. By combining them, that's 6y minus 5y, that is y. Then, minus 2x or negative 2x is similar to plus x. By combining them, that's negative 2x plus x, that is minus x. Therefore, the answer is y minus x. We then now prove that the common difference of this sequence is y minus x. Question: what does it imply if the sequence does not have common difference? That is, the sequence is not arithmetic, because remember, a sequence is said to be arithmetic if it has common difference, because arithmetic sequence is generated by adding a constant d, and that is the common difference. Now, try it on your own. Identify which of the following sequence is arithmetic. You will be given 2 minutes to answer the given problem. 2 minutes, start now. Okay, time's up. Let's now check whether your answer is correct. Number 1. The sequence is 25, 21, 17, 13, and 9. Let's verify whether the sequence has common difference. Based on the solution, we arrive at a common difference of -4. Therefore, the answer is arithmetic. Number 2. The sequence is -20, -13, 1, and 8, and so on. Let's verify whether this sequence has a common difference. So as you can see, there is no common difference because the third term and the second term has difference of 14, which is not the same as the difference of the second term and the first term, as well as the fourth term and the third term. Therefore, the sequence is not arithmetic. Number 3. The given sequence is 1/3, 2/3, 4/3, 8/3, 16/3, and so on. Let's verify if it has common difference. Does it have common difference? It does not have common difference. Therefore, the answer is not. Number 4. The given sequence is 1, 3 halves, 2, 5 halves, and 3, and so on. Let's verify if it has common difference. So as you can see, it has a common difference. Therefore, the answer is arithmetic. Last number. The given sequence is 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. Let's verify if it has common difference. The second term is 2 squared. The first term is 1 squared. You'll need to evaluate first what is the value of each term before you subtract them. 2 squared is 4. 1 squared is 1. 4 minus 1, the answer is 3. Continuing to the second and the third term, 3 squared minus 2 squared, that's 9 minus 4, that is 5. Continuing to the third term and the fourth term, that's 4 squared minus 3 squared, that's 16 minus 9, that is 7. Fifth term minus fourth term, that's 5 squared minus 4 squared, that's 25 minus 16, the answer is 9. So as you can see, the sequence does not have common difference. Therefore, the answer is not. This is not an arithmetic sequence. Let us now continue exploring the relation of arithmetic sequence and linear function. Try it. Generate the first 5 terms of arithmetic sequence whose first term and common difference are given below. Number 1, first term is -5, and the common difference is 10. Number 2, the first term is 25, and the common difference is -3. Afterwards, you are going to answer guided questions for us to analyze the relation of arithmetic sequence and linear function. You can pause the video while you are listing the terms of the sequence. Are you now ready to answer the guide questions? Let's have now the guide questions. First question. Describe the trend or the arrangement of the terms of each sequence. Number 2. Which sequence is increasing? Decreasing. Given the value of common difference, can you describe the trend of the sequence? Let's now answer the guide questions. Number 1. Describe the trend or the arrangement of the terms of each sequence. In number 1, we have the first term of negative 5, and the common difference is 10, arriving at the sequence whose first 5 terms are negative 5, 5, 15, 25, and 35. Number 2, the first term is 25 and the common difference is negative 3, arriving at the first 5 terms of 25, 22, 19, 16, and 13. Can you now describe the trend or the arrangement of the terms of each sequence? As you can see, the first sequence is increasing in trend, increasing in its value, while number 2 is in decreasing trend, or as the terms progress, the value of the terms are decreasing. So, which sequence is increasing or decreasing? So, by answering question number 1, we already answered question number 2. Number 3. Given the value of common difference, can you describe the trend of the sequence? The answer is, an arithmetic sequence is increasing if the common difference has the value greater than 0. And otherwise, it is decreasing if the common difference has the value of less than 0. Let us analyze the relation of arithmetic sequence and linear function. If we consider the relation of n and the nth term, we can think that as a table of values describing the relation of x and y. Having such a statement, we can identify pair of points or points such as 1 and negative 5, 2 and 5, 3 and 15, 4 and 25, 5 and 35. These are the set of points generated by the function or by the sequence. The relation of x and y. If we solve for the slope of this set of points, you will notice that the slope is the same as the value of the common difference. So as we solve the slope, we are going to pick pair of points in able to determine that slope. Let that point be 4 and 25, 4,25 and 3,15. By solving that slope, that is y sub 2, which is 25, minus y sub 1, which is 15, all over x sub 2, which is 4, minus x sub 1, which is 3. By continuous evaluation, That's 25 minus 15, that is 10. 4 minus 3 is 1, and that is 10 over 1, which is 10. The common difference is the same as the value of the slope. And if you can recall, a slope which has value of greater than 0 is an increasing trend. On the other hand, if the value of the slope is less than 0, that determines a decreasing trend. That justifies our answer in questions number 1 and 2. We will do the same process for number 2 to verify that the slope has equal value to common difference. Having the formula for slope as y sub 2 minus y sub 1 over x sub 2 minus x sub 1, again, we will pick pair of points. And for this example, I pick point 2, 22 and 1, 25. Performing the operations above, that is 22 minus 25 over 2 minus 1. 22 minus 25 is negative 3, 2 minus 1 is 1. Negative 3 divided by 1, the answer is negative 3. Therefore, we verify that the slope is equal to negative 3, which has the same value of common difference. Is that clear? By having that activity, we arrive at the conclusion that arithmetic sequence is just like linear function with restricted domain. Let us now proceed to seat work to measure what you have learned in this video. You can pause the video to answer it on your own pace. Identify which of the following is arithmetic and solve for its common difference, if any. Number 1, 35, 32, 29, 26. Number 2, negative 34, negative 64, negative 94, negative 124. And lastly, 7 over 9, 34 over 9, 61 over 9, until 115 over 9. I will just show to you the answers. The answers are, number 1, that is arithmetic sequence which has a common difference of negative 3. Number 2, it is not arithmetic sequence because it does not have common difference. Number 3, that is arithmetic sequence having the common difference of 3. Did you get all the answers correctly? If so, congratulations! For this video lesson, we have learned to define arithmetic sequence correctly. Secondly, we solve for the common difference of an arithmetic sequence. And lastly, we identify which sequence is arithmetic or not. For your homework, study how to solve for the nth term of arithmetic sequence. And what is arithmetic mean? Again, this is Sir JC from Mathfinity reminding you, math is easy when you perceive it positively.